Good afternoon, everyone. Um, if you're online, let me know if the sound's good. Otherwise, hopefully you can all hear me. I'm just noticing my mic here, the batteries are a little low, so if I go silent, just let me know and I'll fix that. Okay, I see the audios are a little extreme there. Hopefully that's a little better. Is that better for online folks? I don't know. It's a little bit different every day. Sometimes it's not good. Is that any better? I'm clipping. Much better. Great. Fantastic. Yeah, my mic seems to be very sensitive to exactly where it's placed on my shirt. So if it's like up closer to my mouth, it doesn't pick up as much, which is a paradox, I guess. But anyway, seems to be working okay now. If you're online, let me know. Thanks. All right, a couple of pieces of business to take care of. We have our first assignment due next week. That's due on the 18th. And I haven't checked lately, but as of like on the weekend, I think there was a couple dozen people already submitted it, which is great to see. That'll be a lot of work on my end for myself and the TA. So I'm making no promises when I'll get those grades back. Just please be confident in the fact that we are working on them. With so many in the class, it does take time to get through all those. And yeah, hopefully it doesn't take too long. Other than that, what I'm planning to do before the end of the week is post the details for the second assignment. And there's only 2 assignments in the course in addition to those weekly, not weekly, per unit quizzes, right? And just keep on top of those, make sure that you're checking the due dates for those things. It'll always be 1 week after we finish the unit in class. If you're working along with us in class, doing the problems as they appear, you shouldn't really have any issue. You should just do them and have no issue at all. All right, so what we are doing right now is we are in the unit discussing the elements of chemistry, which is the title of the unit, where we are kind of taking a bit of a historical perspective here. And what we're doing is we're looking at chemistry, how it arose from its roots in alchemy, Greek philosophy, and how that kind of developed into the science of chemistry. And kind of throughout all this, what I'm trying to preserve as much as possible is the concept of elements, of chemical elements. It's right in the title of the unit. This idea that everything we interact with is composed of fundamental substances that can't be broken down any further. And this idea is a very old one. People understood this to be the case a long time ago. They were a little misguided what those substances actually were, what the nature of them was. You know, they had the 4 classic elements. And only sort of gradually did we discover all of the elements that we know of now. And we talked about a few notable characters throughout history who've made important discoveries with elements. And we're also trying to weave in a couple of important chemical principles that were discovered along the way as well. And we talked about the law of conservation of mass as being one of those where we, that was Lavoisier, and that was a pretty important development as well. So what we're going to be doing now is continuing our journey. We're going to be talking about a few more characters, a few more important discoveries, which is going to lay the foundation for really everything else that we're going to be looking at in the course. The previous people we talked about, we just finished talking about Humphrey Davy. And if you remember him, he was the guy who made the big battery and zapped things with his battery and was able to isolate about a dozen elements using this process by putting an electric current through a number of different substances. The next character we're going to be talking about is John Dalton. And John Dalton was very different from Humphrey Davy. Humphrey Davy, as you remember, was very gregarious. He liked to do fill these lecture halls with people and do demonstrations, and he was very flashy and had a lot of personality. John Dalton, apparently by many reports, was a lot more studious and bookish and not as outgoing, perhaps. But what he did is he proposed a theory of elements. He made a proposal which formed the basis of atomic theory. And this is what he proposed. He said, elements, these pure substances, are made out of atoms, right? This is sort of cementing in that idea that was very old from Democritus back in the Greek days, but was never really understood or was there evidence for this up until much more recent to this proposal. He also says all atoms of a given element are identical. And this might sound familiar from one of our first classes where we talked about, carbon atom from a tree is the same as a carbon atom from a meteor, et cetera, et cetera. The third one, atoms of different elements are different. Fair enough. They can be distinguished by their atomic weights. In other words, so one element, the atoms will weigh different or a different number than atoms of a different element. 4, atoms can combine in various ratios to make compounds. So you can make more complicated chemical structures by taking the individual atoms and pairing them in fixed whole number ratios, right? You can take 3 carbons and 4 oxygens and maybe make something out of that. This was sort of the thinking around that. Last, atoms cannot be created or destroyed. A chemical reaction merely changes their grouping. So you can rearrange them, but you can't really create something new. And, if you think about this, if you think about an atoms as being a little bit like a Lego brick, if you have a bunch of Lego bricks, the individual bricks might be an atom. You can combine them in certain ways to make more complicated structures, which we might call a molecule. They would look different. They'd have different numbers of, little bumps on the top and so on. They'd be distinguishable from each other. A given Lego piece would be identical to all the other Lego pieces that have the same color and shape, more or less. And you can combine them in certain ratios. And if you do a reaction, all you're doing is you're taking apart a Lego structure and building a different structure out of the same pieces. You're not creating new pieces or destroying pieces in the process, ideally. An interesting thing is that there are exceptions to almost all of these rules now that we know of. And it's one interesting thing about maybe scientific researchers in general, when somebody proposes a law or proposes rules like this, almost immediately people start looking for the exceptions. That, this describes almost everything very well, but there are many, many exceptions. So for example, the second one, all atoms of a given element are identical. That's not actually quite true. Atoms of the same element can vary in the number of neutrons, and we would call those different variants isotopes. They're all the same element, but they're not all identical. They have a difference. So when I talked about 2 atoms being identical back in the first unit, I always said if they have the same number of protons, neutrons, and electrons. But you can vary the number of neutrons and still have the same element. Atoms of different elements are different and can be distinguished by their atomic weights. I mean, this is generally true, except it depends how good your measuring device is, because some elements, depending on the isotopes you're looking at, can be extremely similar to each other. Atoms can combine in various ratios to make compounds. I mean, I guess this is true to a point, although there are substances without sort of fixed whole number ratios. And last, atoms cannot be created or destroyed. We actually know that this is definitely possible. We can create them and destroy them. We can't make them really disappear per se, but we can convert one element into another element through a process we call transmutation, which is what the alchemists were after, trying to turn lead into gold. Although we know now when we do this, we need a nuclear reaction to take place. So it's either nuclear fission or nuclear fusion or radioactive decay, one of these other processes, which generally speaking is not going on when we do ordinary chemistry, hopefully. So John Dalton came back. He proposed, well, he listed the elements that were known when he was, making this proposal, and he made up all these kind of neat symbols for each one of them, which you can see there on the right. That's the list of the known elements. The weight is the relative weights of each of these relative to each other, as was understood at the time. Measurements at the time were not as careful and as accurate as what we have today. So we know, for example, if hydrogen's 1, carbon is 6, they have it in the table as 5. So there's some similarities. Actually, carbon's not 6. Carbon is 12. Carbon's 12 times. So actually, some of them are quite a bit off. I think that comes about because hydrogen actually appears in nature as H2, not just H, and they didn't know that. So they had hydrogen is weighing double what it actually weighs. So he tried to get these numbers out, and he tried to say that this was a fundamental property of each individual element, and made these cool symbols. Another chemist came along after him named Jöns Jacob Berzelius, and he proposed a simpler notation. While those symbols were maybe fun and attractive looking and they look cool, he thought they're too complex, they're too difficult to memorize, and he just said, why don't we just use the letter for the element? So hydrogen can be H, oxygen can be O, nitrogen can be N, and so on. And this is sort of what caught on. So we usually just use the first letter of an element to be its symbol. Now, clearly we have some elements that, we might have one letter where there's more than one element. So N, as an example, there's nitrogen, there's also nickel, there's niobium, there's a whole bunch of other N elements. So then usually there's either one letter or two letters. He also proposed a notation if you have a compound, like water, where you have more than one element together, a couple of atoms together, and you have, in this example, H2O. That means there's two hydrogens and one oxygen, and he proposed the number after the symbol in a superscript would be the number of that number of atoms of that type in the compound. And that's very close to what we still use today, except instead of a superscript now we use a subscript. So it's below instead of up. So this was proposed as far back as then. I see a question in the chat from Tori. What's potash? I think potash is potassium oxide, K2O. There you go. Completely unrelated. Okay, so here's a picture of the periodic table by the time Berzelius did his stuff. You can see the known elements. All the black ones were the ones that were known way back, like into Roman times. Things like lead, things like gold are on this list. The ones that were added by Davy are in blue, and the ones that were added by Berzelius are in red. He managed to discover a few more. And what you're starting to see maybe is our modern periodic table that I put in here is starting to fill out, right? We have certainly lots of gaps still, but people were thinking really hard about all this list of elements. You know, they thought it's not just coincidence that we have all these different elements and they're all unique somehow. There must be some pattern, or there must be some underlying principle which governs all of this, which people didn't understand at the time. There must be a reason why we have boron and carbon and we don't have something halfway in between. All right, so we have a couple of questions to hit before we get too far. Humphrey Davy isolated many new elements by putting what into containers of molten salts? Frog legs, terminals of a large battery, carbon powder, or his finger. Berzelius discovered some new elements, lithium, silicon, vanadium, and selenium, and obtained more accurate weights for several elements. He proposed chemical notation using superscripts. So for example, we would use for water H2O. What does the subscript 2 indicate in this formula? 2 hydrogens are required to equal the mass of 1 oxygen. The ratio of elements in water is 2 parts oxygen to 1 part hydrogen. C, 1 hydrogen atom makes 2 bonds to 1 oxygen atom. Or D, the ratio of elements in water is 2 parts hydrogen to 1 part oxygen. So I saw some nodding on D there. So yeah, we're good. All right, so here's where we're at. We have this periodic table, or at least we're starting to generate a list of elements which put on a modern table would fill it maybe halfway. And people were very curious about the relationship between the elements. And what people notice almost right away, and when you think about the chemists of these days, they probably in certain ways knew more about the chemistry of different substances than modern chemists do. Because they spent a lot of time interacting with these things, spending time trying them, mixing them with different things, trying to see what was going on. where I think a lot of chemists don't do that anymore. It's like you might learn it out of a book or so on, but you probably have never tried it yourself. But what they found is, that a very observant, keen eye, they noticed that there were certain elements that behaved very similarly when put in the same situation. So here's an example of a list of elements that we now know form a family. If you take lithium metal, and you can find lithium metal in lithium batteries, you can open up the battery and find pieces of lithium metal. If you take that metal, it's like a foil, and you drop it in water, what happens, and you can kind of see it in this picture, but it's frame rate's pretty bad. It'll fizz around, it'll react with the water, it'll dissolve, it'll turn into lithium cations, which are dissolved in the water, and it makes a gas. And that gas is hydrogen gas, so it bubbles as it's fizzing around on the surface of the water. It's not super spectacular, this reaction, but it will fizz until the metal disappears, and then it's gone. If you go down to the next one in the list, you get sodium metal. You get metallic sodium, which is very soft metal. You can cut it with a knife and drop a piece in water. It'll do the same thing, except it's much more reactive. It'll fizz around very rapidly. It'll make hydrogen gas, and it'll give off enough heat that the hydrogen gas can actually catch on fire, like you see in this picture. And the flames are actually a really nice yellow color, and that's characteristic of sodium. Sodium, when heated in a fire, gives that color. They used to use for street lights, sodium lights they were called. They put sodium metal in the street light and vaporize it, heat it up, and it would create this characteristic sort of yellowish orange light. They mostly use LEDs now. They're much more environmentally friendly, use a lot less energy. Keep going down, you could take potassium metal, and potassium metal is much more reactive than sodium. So it'll do the same thing. It'll fizz around, it'll dissolve, it'll make gas, hydrogen gas, and catch on fire. And you can see that the flames in this particular picture are kind of, I don't know if you can tell, they're kind of violet in color, kind of a purple-violet color, which is very characteristic of potassium in fire as well. And you can keep going down the periodic table. You can take rubidium, and rubidium does the same thing, except it's, again, much more reactive. So what they notice is they all do the same chemistry. They all do the same reactions. They all react with water to make ions and hydrogen gas, but they go from sort of least reactive at the top of the list down to most reactive going down. So the important thing here is they recognize there are certain groups of elements that do almost the exact same thing when you put them in the same situation. Maybe at different rates, maybe give off different amounts of energy or whatever, but they do very similar chemical reactions. So they're seeing relationships between the elements. They aren't all just completely independent, unique things. So people spent a lot of time trying to figure out what these relationships might be. And one guy, Dobereiner, in 1850, published what he called his triads, that he could find these groups of 3 elements, which all had a very interesting property, that if you take the weight of the first one and the weight of the third one, and the average of those 2 was the weight of the middle one. And they worked out almost exactly for many of these different families. And what he found is these 3 elements that were in these triads showed similar kinds of chemistry. They did similar kinds of reactions. They behaved similarly when you put them in water or exposed them to oxygen gas or whatever it was that they were testing these against. And he found several such triads. And if you pick those triads out of a modern periodic table, like you might be able to see in the little image here, what they noticed, or what they didn't notice it because they didn't have a modern periodic table, but those triads all form spots where 3 elements are vertically ordered on the modern periodic table. So they're finding these relationships. Newland in 1864 proposed something quite interesting. He recognized that in music, you have a scale and you can have, like a middle C, say, in the scale, and then you go up the alphabet, C, D, E, F. And what happens is once you hit G, you start back again at A, and then A, B, C, D. And so we might say that, a C, that's middle C on a music scale versus the next C up, we would call them octaves. It's the same note, but different frequencies, right? And they saw the same sort of pattern with elements. Is you have hydrogen, then you have the next one, which is lithium, and then so on and so on. They all seem kind of different in their own thing, but then once you got to 8, all right. I'm going to fix my mic because I went silent here, and there we go. Hopefully that is sounds okay to you guys. Might not be. Actually, tell me if it's better. Because if my mic is actually not as good, then it's good to know. I knew I was playing with fire. The mic was low when I started. All right. So this idea then of octaves works quite well for the early elements, but then as you can see, once you get to about iron, it kind of starts going all over the place. It's not following a scale very nicely anymore, and so for that reason, there's maybe something to this, but it didn't quite exactly match what they were hoping to see. Thanks everyone for letting me know that my mic died on me there. Naquet, 1864, same year. He proposed that there are families and that you can organize all the known elements into different families, where the first family he had chlorine, bromine, iodine, and hydrogen. And he had a bunch of different families. Some families were all metals, which he puts on the bottom. The others were all metalloids, which are up on the top. And he was trying to organize them in some way which, preserved this relationship that they knew of in terms of their chemistry. So a lot of people were working on this, and a lot was being discovered when finally the person to kind of finish and put this all together was a Russian scientist by the name of Dmitry Mendeleev. And he did this in the late 1800s, and what he was able to do was take all known elements and organize all of them into a single table, not just maybe like a list with, a list with families or picking out triads here and there. He started out with this block of 9 elements and built the table that we now know and love, and put all the additional elements that were known at the time into it. Now, it's remarkable what he was able to do for 2 reasons. One is most of the elements, roughly half or maybe not quite half, many of the elements were not discovered yet. So he was trying to design this table. He was trying to organize all these things with an incomplete set, right? So he knew there was gaps. He knew there was probably other ones, and he had to leave spaces, empty spots on his table for the as yet undiscovered elements. The other thing is he organized them based on their masses, and he realized that his table was never going to work using the masses that were understood to be correct at the time. So what he did is he realized, no, this element doesn't fit here. This element should fit there. So they must have measured the mass wrong. So he started monkeying a little bit with the masses that had been known at the time for the elements to make them fit into his table. So then he published it, and basically silence, right? He was just one of many who were publishing all kinds of theories about how these might be related, what the relationships might be. And it wasn't for a few years until he really became famous. And the reason for this is because with all those empty spots he left on his table, what he was able to do was predict all of the properties based on his understanding of the existing elements, where they belonged on the table. He was able to predict the blanks. He was able to predict their chemical properties. He was able to predict their mass, things like density, whether they were a metal or not a metal or a gas or whatever it was. And so he had, these sort of temporary names for all these as yet undiscovered elements. So what happened is there was one sort of blank spot, one hole in his periodic table right underneath aluminum. Aluminum was well known, but the one under it was not. And Mendeleev, in his proposal, I spelled his name wrong there. Mendeleev. No, it's Mendeleev. He proposed that blank spot under aluminum might be named Eka aluminum, or it's like aluminum. He proposed it should have an atomic weight of 68 and a density of 5.9 grams per mil. It was discovered a few years later. It has the name now gallium, named after where it was discovered in France. Its mass is 69.7, which is very close to his prediction of 68, and its density is exactly 5.9 grams per mil. So this is when people paid attention. They said, wow, he's actually predicting elements that we don't know. There's something deeper, correct. There's something more to his table that we didn't know before, and what no one else's proposals were able to do. Make predictions about the as yet undiscovered elements. This is what he says. Before the promulgation of this law, chemical elements were mere fragmentary incidental facts in nature. There was no special reason to expect the discovery of new elements. Right? So people might discover a new one, great, add it to the list, but they had no idea how many there were supposed to be, how close they were to getting all of them, where he's like, no, I know where they all are, I know where all the blanks are, we just got to fill in these spots, and our periodic table is complete. So once people kind of realized that he was onto something here, it led to a lot of interest in people trying to discover the remaining ones, fill in all the blanks on the periodic table, which we've actually successfully done by now. In fact, the last 4 elements that were added like, I think, 2017. They were officially registered in the periodic table by IUPAC. So everything was going great for Mendeleev. He was very well respected. His stock was rising, as it were. Until 1894, there came a threat to his table. There was a British scientist named Lord Rayleigh, and he isolated some substance from air. It was present in air, and he proposed it was a new substance, a new element. It wasn't like any other element. He wasn't able to break it down into anything simpler, and he gave it a name. He said, we'll call it argon. Actually, I don't know if he called it argon or if it was called argon later, but the element is what we know now today as argon gas. There was no spot on Mendeleev's table for argon. So Mendeleev said, it's not real. You're either faking your results or you're measuring something wrong. You're incorrect because I have utmost confidence in my periodic table and there's no blank for argon. So you're wrong. Basically what his response was. But it turns out he was not wrong. There was an element argon. It does exist. It makes up almost 1% of the air that we're breathing, so it's not even really rare. And very shortly after the discovery of argon, several other components were purified out of air that were very unreactive, which explains why it took so long for people to discover them. Because they were so unreactive, people couldn't use chemistry. They couldn't form compounds with them. They couldn't isolate them in the ordinary ways that people were used to using in order to isolate elements in the past. But it's definitely true. We have all these elements that you see here. They're in glass tubes with electricity put through. And we can create lights with each of these different elements. And neon, of course, most famous for neon lights, neon signs. And all of these are elements. And what it turns out to have been the case is none of these elements were known at the time of Mendeleev's periodic table. There was a whole column left out of his table. He didn't have any blanks, but at the edge of the table, there needed to be a new column added, which all of these elements fit into. So it wasn't like argon was some random element somewhere in the middle that he needed to have a blank for. It was like a whole new column. And this is a nice example maybe of like a scientific theory which was not incorrect, but it was also not complete. And then more discoveries after the initial proposal from Mendeleev allowed not the theory to be thrown out, but for it to be modified, to have it grown, have it enriched, to include that new discovery as well. So we have our current periodic table. There's nothing to say that we may not make discoveries in the future that will modify that further. Maybe there's new rows we add, or who knows. Question. What is not true of Mendeleev's periodic table? This is one of his early sketches. A, it corrected the atomic weights of some known elements. B, it predicted the existence of the noble gases. C, it organized the elements based on their reactivity. D, it left gaps for elements that were not yet discovered. So one of those is not correct, which is B. Great. All right, just a few other little things to throw in here before the 1900s came. When you think about it, 150 years ago is kind of the time frame that we're in. That wasn't that long ago. It might seem like ancient history, but the amount of understanding, how our understanding of chemistry has improved in the last 150 years, it's a relatively young science compared to something like, I don't know, math. A lot of mathematical principles were discovered or found a lot earlier than in chemistry. 1897, a scientist by the name of J.J. Thomson, he was a physicist. He discovered that he could make a device which would create a stream of these particles that could be bent by a magnetic field. The stream could be bent, deflected by a magnetic field. He called these particles corpuscles, which we now know are actually called electrons. He said they were very, very light. They weighed 1,000 times less than the smallest atom, which is a hydrogen atom. And he said that these must be coming out of atoms. And he said that these electrons must be in all atoms, and that there also must be something else in the atoms with a positive charge that balances out the negative charge of the electrons. So they're starting at this point in time to discover the subatomic particles, which we know are protons, neutrons, and electrons. So the electron came first. Protons came second in 1911 by Rutherford, and he did a very famous experiment with a very thin sheet of gold foil where he shot alpha particles, which are, if you have a radioactive source, it'll shoot basically little nuclei that are helium atom nuclei. And he noticed that some would go right through the foil, some would bounce back. And what he discovered from that is that atoms aren't uniform, that they have all of the mass, essentially all the mass, compacted into a very tight ball in the center. And most of the volume is empty space. So the electrons take up a lot of space on the outside of the atoms, with the protons and neutrons concentrated in the center in what we call the nucleus. So that was pretty important, 1911. Who was the guy, I forget now, who came up with a neutron? That came later. I don't know. I don't have a slide for him. Something else which was taking place at the time, which led to the discovery of a whole host of new elements, first of all came in 1896. There was a scientist by the name of Roentgen who discovered X-rays. And he discovered this by, he discovered that certain substances or certain energy sources could give off these light rays. He knew they were a type of light, but he didn't know what they were called. So they just called them X-rays. There's some kind of ray, and just like in math, if we have an unknown, we often use X. We just call them X-rays. Becquerel, who was another scientist, discovered he had samples of uranium. And in those days, if you wanted to take a photograph of something, you didn't use like a cell phone camera, obviously, with a CCD. They had film, and the film was based on, typically there were glass plates that were coated in a silver solution, and when they absorbed light, it would cause that to turn black. So basically you were making a negative, and by putting it in the presence of light, you could cause that color change, and you could develop photographs that way. He had a drawer, so if you have these plates, and if anyone has done amateur photography with the actual dark room and all that sort of thing, you got to be very careful not to let light develop these films before. You got to keep it very, very dark. So he had a drawer where he kept all these film plates, and he put inside his sample of uranium just because he ran out of space. And then a while later, he went to retrieve his glass plates and realized they were all developed. And he's like, how could these have been developed if they were kept in the dark, away from light? And it clicked in his head that something being given off by this uranium sample was causing those to be developed. And he said, this must be some kind of light. It must be these X-rays that we're talking about. And these can be emitted by just pure element substances without putting electricity in them or anything like that. They were just on their own giving off this light. So work began with a husband-wife team, the Curies, Henri and Marie Curie, and they started working with these substances that were found to be giving off these X-rays. And in 1897, they discovered thorium, which was another recently discovered element, also gives off X-rays. And they could take pitchblende, which they knew was sort of just this mixture. It was a kind of rock, but it was a mixture of a whole bunch of different things. And they knew it was radioactive, and they could purify it, using chemical techniques. They could dissolve away certain substances, concentrate it, and make a concentrate that was 4 times more radioactive than pure uranium. So what that told them was it's not uranium in this sample that's causing it to be radioactive. Because pure uranium, they knew its radioactivity was a certain number. This concentrate was 4 times bigger than that. So something much more radioactive gives off much more X-rays than uranium was present in that concentrate that they were making. So they went to work and they kept concentrating and doing chemistry and crystallizing, and they did a crazy amount of chemistry here, and they were eventually able to make a concentrate 400 times more radioactive than pure uranium metal. And they say this in their publication: we believe the substance that we have extracted from pitchblende contains a metal not yet observed, related to bismuth by its analytical properties. So they kind of knew around where it should belong in the periodic table, which is well known by then. If the existence of this new metal is confirmed, we propose to call it polonium from the name of the original country of one of us. And that was Marie Curie's original country, which was Poland, where she grew up, although both of them at the time were working in France, in Paris. They continued their purification, they removed the polonium, and they found a separate substance that wasn't polonium, which was 1,000 times more radioactive than pure uranium, and they called it radium. Now, radium is a very interesting substance. People found ways of applying, came up with applications of radium very, very quickly. What they discovered is that if you take certain kinds of pigments and you mix them with uranium, the radium, the X-rays being given off by the uranium can be partly absorbed by the pigments, and it makes the pigments glow. So basically what it did is it made glow-in-the-dark paint, and what they started to do was make clocks. Remember, there's limited or no electricity widespread at the time. They could paint clocks and watches with the numbers and the hands so that you could tell time at night, which was kind of a big deal at the time. The only other way to do it, I guess, was light a candle and hold it up near the clock. Now you could do it anytime. There was a company actually in New Jersey that did a lot of this work. I forget the name of it. It was like the American Radium Watch Company or something like that. And what they would often do is hire typically young women right out of high school. They would give them jobs where what they were to do is with a paintbrush, mix up this paint and apply it on the watch faces. Or if they were luckier, I guess the clocks, which are a little bit bigger and easier to do. But you needed a very, very fine-tipped paintbrush. And what they would often do is to keep the threads, the hairs of the paintbrush in a tight little piece so it didn't get all frayed, is after they would paint for a while, they would often lick the tip of the the paintbrush to kind of bring it all back together. And they would paint. It was very, very careful, painstaking work that they had to do. Given their age as well, they were like out of high school, they had jobs, they had money. In many cases, they were single. They liked to go out, liked to party, they liked to have drinks, etc., etc. And what they would often do is take this paint and they would paint their nails before they went out with it. They could go to a dark place and it'd be shiny. Some of them would paint their teeth, right? And so you'd have these bright, shiny teeth, which would be kind of just an interesting thing. They had no concept that radium, nobody did at the time, no concept that radium had very devastating health consequences. Radium is especially bad because you find radium in the same column of the periodic table as calcium. And our body is very good at scavenging calcium from our diet and incorporating it into our bones, into our skeletons. And our bodies are not very good at distinguishing calcium and radium because they have very similar chemical properties. So what happens is if you expose yourself to a lot of uranium, your body grabs that uranium and sticks it in your skeleton. So it's not like you just get exposed to it once and you excrete it. You get exposed to it and it stays in your body for a long time. Because they had these radioactive elements in their bodies, many of them died, many of them developed cancer, radiation poisoning, all these sorts of things, which are typically long-term things that you only notice a little bit down the line. So there was very, very devastating consequences for the women working, painting these watches. So right around this time, I think it was 1901 or 1902, the Nobel Prizes were founded. I think 1902 was the first Nobel Prize in physics. In 1903, the Nobel Prize in physics went to Marie Curie, all by herself. And at that point in time, there was perfect male-female gender parity for Nobel Prizes in physics, 1-to-1. There was one in each year, 1902, 1903. Marie Curie got it all by herself, though, which is funny if you look at it, because her husband, they worked as a team. They worked together the whole way through, and he wasn't included on the Nobel Prize at all. And can you guess why that was? Well, there's one very simple fact. To get a Nobel Prize, you have to be alive. Her husband died before the Nobel Prizes were awarded. Therefore, there's no way he can get one. You can't get a Nobel Prize if you're dead. Actually, that's not quite true. There's one way you can be dead and still get a Nobel Prize. That's if you're alive when the prizes are announced. And then usually it's a few weeks later that the ceremony happens and you physically get your prize. If you die in that few week period, then they don't take it away and give it to somebody different. You still get it posthumously. But he wasn't so lucky. You might think, these people spend hours and hours every day working with highly radioactive materials. You might think, well, how do you think this guy died? Radiation poisoning? No, he died, it's very curious actually, he died of a traffic accident, which you might say, well, that's not maybe that rare, but it was very rare in 1900 because cars weren't really invented yet. Maybe they were invented, but they certainly weren't widespread. There wasn't traffic in the streets. Traffic was still, in that time, horse and buggies, and he was actually trampled in the street by a horse and buggy. That's how he died, which doesn't sound like a very nice way to go. So yeah, she was by herself and she got the Nobel Prize. Actually, later on, her daughter got a Nobel Prize as well. Maybe she got hers in chemistry, though. So 1905, after Marie Curie and her husband, to some extent at least, before he died, contributed a lot by discovering a number of elements that were radioactive, including radium and polonium were probably the major two, as well as a few other ones. Uranium and thorium were discovered as well. And you can see in the periodic table, there's still a couple of blanks, but for the most part, certainly the first, 50 or so elements are all discovered. And the blanks are kind of at the bottom end of the periodic table. And yeah, so that was, 115 years ago, 116 years ago. We more or less had a working copy of the periodic table. If you've taken chem, and first year chem, and you're doing reactions, calculations, stoichiometry, all that kind of stuff we do in first year chem, you may not have ever used any of the ones that were not yet discovered by 1905. In fact, if you worked in a lab, you probably haven't used many of these elements, although you've probably been exposed to them. Radium wasn't known yet, not radium, radon gas, which is on the rightmost. It's underneath Xn, which is xenon. Another question, who discovered the electron? Was that Rutherford, Mendeleev, Curie, or J.J. Thomson? So we know Rutherford was the nucleus, protons. Mendeleev was the periodic table. Curie was a number of radioactive elements. And Thomson was the electron. What element was discovered by Marie Curie and ultimately named after her country of birth? Francium, polonium, germanium, americium. And that's how you pronounce that element. It should be, looks like it maybe should be like americium or something, because like it's America, but it's americium is the way you pronounce that, which I always found a little unusual. All of these are named after countries, and francium might be a good guess because she did most of her work in France, but her country of birth was actually Poland, and polonium is the correct answer to 4.9. All right, this is our modern periodic table. This is what we understand the periodic table to look like today. Notice that at the bottom, there's those kind of two rows that are kind of floating down there. They're like, it's like when you see a map of the US and you have Hawaii floating off. It's not connected to the rest of them. Those two rows actually do belong, like where you see in the table, there's like two asterisks, like a single and then a double. That whole kind of double row needs to be slotted in there, and the whole table is like a lot wider. So that's actually where that goes. When you see them floating down there, it's only because you'd have this weird aspect ratio. So they pull them out, pull them down, compress it in, and make it look kind of more like, I don't know, aspect ratio we're used to seeing on a sheet of paper. I will point out, and I'm not going to go through the discovery of all these elements down below, most of the elements in the bottom couple rows are what we call synthetic elements, meaning that they don't exist in nature. And often they're generated in a particle accelerator by smashing two lighter nuclei together. They're detected, they might exist for fractions of a second, and then they disappear, which is why they don't appear in nature. They just decompose way too quickly for them to accumulate and be found in natural samples. So that's true for a lot of these, which, they're maybe interesting from a theoretical perspective, but they're not interesting from from the point of view that we can use these elements to build things or create new medicines or whatever. They're more curiosities of physics and help us understand theories and nuclear structure, all this kind of stuff, as opposed to, things we do chemical reactions with. A few exceptions, like 92 there is uranium. Uranium, of course, is naturally occurring and the source of nuclear fuels, nuclear weapons. Uranium, actually, the two bombs that were dropped on Japan in World War II, one of them was a uranium bomb, and the other one was plutonium, which is next to, two over, I guess, from uranium. So plutonium is a synthetic element. It's actually made from uranium. And so we have methods, we have nuclear methods of converting sometimes some elements into others. Although it's not easy to do. It's not a feasible way of making more gold, for example. Okay, one other piece of information that I wanted to talk about was another discovery, I guess, or proposal, which has come to be adopted back in 1909. And it was done by a scientist by the name of Jean Perrin, or Perrin. And it's called Avogadro's constant. And it's actually, Avogadro had nothing to do with this. He was long dead. He died in 1856. Avogadro's constant didn't come about until 1909. So this was named in his honor, as opposed to named as a discovery after him. So, which is interesting because anyone who's taken high school chem and first year chem probably knows, has heard of Avogadro's constant or Avogadro's number, when this guy could have been like famous through eternity if he put his own name on it. Perrin's constant. I don't know. That's a nice picture there of Avogadro. Might want my money back if I paid for that. Okay, so what Avogadro's constant was is as it was defined back in 1909, and actually it was just redefined, I think 3 years ago. We always like to change things just a little. It was defined as the exact number of atoms that could be found in exactly 12 grams of carbon, which is approximately 6 times 10 to the power of 23. Very, very large number. It's such a large number that we can't really comprehend of it. It's too big. It's bigger than anything we've ever experienced in our own lives. When I say that was redefined, it was redefined, I guess, because people realized that we'd never know. We can't exactly measure 12.000 with infinite zeros of carbon. And if we can't measure that exactly, we also, even if we could measure that exactly, we couldn't exactly count the number of atoms that were in there. So there's some uncertainty exactly what the precise number was. So we only really know very well the first 5 or 6 digits of it. So what they just said is, well, we'll just cut it off after 5 or 6 digits and say that's the number now. Even like, it's 6.022051694, and it would just go on until you get to 23 places after the decimal. Said, let's cut off the last 15 digits or so and just use what we know very well. So it's not exactly anymore the number of atoms in exactly 12 grams of carbon, but it's pretty damn close. So this number, to give you an idea of how large it is, the world GDP in 2014 was 80 trillion US dollars, if you converted everything to US. So this is, you added up all the salaries of everybody in the world in 2014, you get 80 trillion, which is 8 times 10 to the power of 13 US dollars. Avogadro's constant is this much money in dollars times 7.5 billion. So if people were producing that much money for 7.5 billion years, that number of dollars would be 1 Avogadro's constant, which we sometimes also call the mole. Okay, the Avogadro's constant is also called a mole. That's 1 mole of dollars, which is a pretty big number. Considering, 12 grams of carbon is like a small amount that you could fit in your hand very, very easily. The number of atoms in there is a staggeringly large number, meaning these atoms individually are super, super tiny. Another way of thinking about it is if you took peas and you could somehow get a mole of peas, 6 times 10 to the power of 23, it would coat the entire Earth 1/2 a kilometer thick of peas. Which might give you maybe a bit of an idea of how many that is. Very, very large number. Imagine, what would it be like to live on a planet that was a kilometer deep? Like I was out this morning actually snowshoeing, and if the snow is kind of crunchy, you can stay on top. But now it's really fluffy and you still sink in. Like with snowshoes, if you're on the top of a 1/2 kilometer of just peas, how deep would you go down? I don't know. We have to do this experiment. Okay, so what does Avogadro's number represent? Also called a mole. Is it the number of atoms in 12 grams of pure carbon? Is it the number of molecules on Earth? Is it the number of peas needed to cover the Earth? Or is it the number of atoms in a molecule? The answer is A. Almost exactly. It's very close to the number of atoms in exactly 12 grams of pure carbon. Great. So I want to take this concept of the mole and apply it to maybe a more modern concept. There's a type of alternative therapy called homeopathy, which was developed in 1796 in France by someone named Samuel Hahnemann. And this was sort of developed as a possible kind of a medical intervention, a way of healing people. And to put this in its correct historic context, medical science was really not very advanced in 1796. In fact, many of the practices that were done in so-called mainstream science back in 1796 were probably nothing short of horrific. There were certainly lots of sort of experimental types of surgery. If someone had chronic headaches, you might maybe, I don't know, drill a hole in their skull and see if that helps. And very weak understanding, very low amount of scientific method put on different treatments, and no anesthetic developed at the time, no painkillers, except alcohol is probably the only thing going at the time. So really it was the Wild West of medicine, not the time you want to be in if you develop some sort of medical issue. Now is much, much better time. So compared to many of the other, I guess, available remedies, homeopathy was probably had better outcomes than many other systems, just because by its nature it was not doing damage to the people that were using it. Homeopathy became very popular after it was introduced. It was based on sort of two main principles. The first principle is that like cures like. The idea being that if some substance causes some negative side effect, so let's say, for example, you take poison ivy and you rub it on your arm, you'll get a rash. Or if you eat rotten meat, you'll get sick and you'll vomit. You know, the idea is if you take that same substance that caused the negative side effect and you dilute it, it'll then cure that same side effect from some other cause. So the thinking is, like, if you take, let's say you get a rash that's caused by poison ivy. If you take poison ivy and grind it up, dissolve it in water, and then dilute that to an extremely dilute level, you could then put that on your rash and it would heal it. So this is not true. Like there's no evidence that this is actually the case, but it is sort of one of the foundational beliefs in this system of therapy. So you take something that causes a negative symptom and then you extremely dilute it. And when I say dilute it, they'd use a process called serial dilution, which means you dilute it once by maybe a factor of 10 or a factor of 100. Take the resulting diluted solution, dilute it again by a factor of 10 or a factor of 100. So if you dilute it by a factor of 100 twice, you've effectively diluted it by a factor of 10,000. But they wouldn't stop there. They would keep diluting, 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 diluting until you have an extremely dilute solution that we'll look at in a minute. So potency, the idea is that the more you dilute it, the more potent it becomes, which is sort of the opposite of what we talked about in our first unit, which is the dose makes the poison, right? The bigger the dose, the bigger the impact it'll have on you. And that's kind of logical, like that might be the case. But the belief in homeopathy is the opposite, that the more you dilute it, the more active or the more potent it becomes. So potency is given in units of C, where a C is a factor of 100 dilution. So if you had 2C, that means you diluted it by a factor of 100 twice, and that would have a concentration 1/10,000th the concentration of the original dose. So yeah, this is my pun, serial dilution. So you can dilute it serially. One other thing I didn't mention is that in between each of these dilutions, important to the thing is a process called succussion, which means you mix the diluted material, but you have to mix it in a very specific way. And it usually means banging a container of the mixture against a slightly elastic surface. So you're kind of going thud, 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 and that's shaking it. And it's believed that in order for the healing properties to transmit through the dilutions, you have to mix it in that very certain way, which harkens back to a belief that the alchemists had. They believed that you had to stir a reaction a very specific way, or you might have to use, in their example, magic words or some other more sort of a ritualistic aspect to the mixing or to the work to make it have the intended outcome. All right, so I did a serial dilution here in my lab. This is just using blue food coloring. And so you can see 0C would be like what's sometimes called the mother tincture, which is the concentrated starting sample, diluted by a factor of 100, diluted again by a factor of 100 to get the 2C, and you see how very dilute that's looking. 3C, 4C, 5C, 6C. You can't really see it anymore after about maybe 4C. Dilutes away extremely quickly. So in homeopathy, if you go on Amazon right now and you Google homeopathic pills or treatments, you can see like this is one container that you can buy on Amazon called the Homeopathic Remedy Chest. These are all 15C. So it's been diluted by a factor of 115 times in a row. And then what they do is they take the resulting solution and put one drop onto like a sugar pill and let it absorb into the sugar pill and then let it dry out. And they put the pills in the bottle. So you're not actually taking the solution anymore. You're taking a pill that was in contact with the liquid that dried it out. So if you think about it, when you dilute anything down that much, it's going to have, the dose is so extremely low that it's, our understanding of toxicology, it's not going to have any biological impact on you. So from that perspective, it was probably safer than many of the existing medical interventions available in 1796. So it didn't cause any harm. Another example, just to give you an idea of what this serial dilution does, if you take very concentrated salt water, which we call brine, 36% salt by weight. Seawater is not quite 1C, it's like 3%. Tears are getting close to 1C. Once it's at 1.5C, your tongue can't taste the salt in the water anymore. It's too dilute. If you keep diluting it by about 7C, that's the salt concentration of one teardrop dissolved in a body of water the volume of an Olympic swimming pool. 10C was one teardrop dissolved in a volume equal to Lake Ontario. 12.5, one teardrop in the Atlantic Ocean. 14.5C was one teardrop dissolved in a volume of the planet Earth water. If you could get pure water to that volume. 15C was what they were selling as the remedies in that remedy chest on Amazon, which I think is still there. So while this was very popular in the early 1800s, along came Avogadro's constant in 1909 and basically demolished homeopathy, because people quickly realized how many atoms you can find in a certain amount of water or any other substance, and kind of did the math and said, there's no way there's a single atom of the original material in the final diluted solution, right? In fact, you can kind of work it out. Somewhere between 10 and 11C for salt, there's less than a 50-50 chance of finding a single atom of salt in a 1 milliliter sample. So by the time you get to 15, there's an extremely small chance that there's a single atom of the original salt in that final material. So people realize, well, there's nothing in here. It's just water at that point. This can't be really doing anything. This stuff's not cheap either. Like here's one. It's $235 a couple of years ago. And it'd be interesting to look around and see what you can get these for. So these, you know, there's a whole bunch of bottles in there. They contain all sorts of different things from, you know, who knows? Anything sort of poisonous, could be arsenic, could be whatever. Take that because it causes a negative effect. You dilute it down until there's nothing left. Put it on the pill and dry it out. Yeah. This is one of the ones, and you can actually buy these around here. You can buy them in grocery stores. You can buy them in pharmacies. It's called Oscillococcinum, which is a mythical bacterium. It's a type of bacteria. It's got the name that bacteria have, but there's no such bacteria ever discovered that has been given this name. It's for treating flu-like symptoms, and you see at the bottom left, it says homeopathic medicine. If you flip the box around, you can see that they take Anis barbaris hepatitis, and they dilute it 200C. So what they do is they take the liver of a duck and they grind it up, and that's the original substance. Then they start diluting that by a factor of 100, and they do it 200 times in a row. So 15 is enough to make sure there's none of the original substance present. 200 is definitely going to do it. So 200 is way out there. 50C is around one teardrop worth of salt dissolved in a volume of water equal to the volume of the universe. There's definitely none in that 200C sample. So how could this possibly work if there's no substance in it? And there's all kinds of theories that are out there. People say, like, well, it works because of this idea of water memory is something that some people will say. That water, yeah, there may not be any of that molecule in the water, but the water remembers a time in the past where it was in contact with it. And we know this isn't true. You know, I know in Frozen they do have water memory, but in the real world we don't. Or I should say, water does have memory, but it forgets quickly. It forgets in about 10 to the minus 13 seconds. So in like femtoseconds, it forgets what it was in contact with. So this is not, from a scientific perspective, a plausible explanation for how homeopathy could work. I guess the question is, does it even work? There's been a few systematic reviews where people have tried to see if it works or not. The British Journal of Clinical Pharmacology says there was no homeopathic remedy that was demonstrated to yield clinical effects that are convincingly different from placebo. It is concluded that the best clinical evidence for homeopathy available to date does not warrant positive recommendations for its use in clinical practice. A very similar statement from The Lancet, which is interesting. They both say it doesn't work any differently from a placebo, but that's not to say a placebo doesn't work. There's actually, it's very well known in medicine, it's called the placebo effect, that often if you give someone a placebo, which is a substance which is known to have no beneficial effects on your body, many people just psychologically will report relieved symptoms because they feel like they've done something to take control of their health situation. It's not going to work for something like a strep throat where you have measurable infection, but for things more like chronic pain or things like that, where it's maybe your symptoms are subjective to a certain extent, people do report with a placebo, and they report the exact same things with homeopathy as well. Real issue, though, is when homeopathy sort of oversteps beyond those sorts of things and tries to replace legitimate medications that we need to retain our health. Like we saw something similar with Steve Jobs back when we talked about his cancer treatments. No-sodes are a kind of homeopathic treatment which people are selling as alternatives to vaccines. They don't work at all like a vaccine works. It doesn't elicit an immune response that gives you protection, but that certainly does not stop people from selling it. And there's a regulatory loophole in Canada where these aren't considered medicines. So medicines, to be approved for sale in Canada, need to be shown to be both safe and effective. These are considered supplements. They're not considered medicines, so they only need to be shown to be considered safe. And they are safe from the perspective that they don't really contain anything in there except water. But they're not safe from the perspective that they're causing people to make bad decisions by foregoing things like vaccines, which are necessary for good health. Here's Robert Strang before he was famous. He was still the Chief Public Health Officer of Nova Scotia. He says, "Our position would be, why would we even have these on the market? There's no evidence they're effective and they can do significant damage by the perception that they're an acceptable alternative to immunization, especially at a time when we have significant issues in our vaccine coverage rates." And this is still going on, and more so with COVID, because as we know, we're in the middle of a point in time where we're scrambling to get enough vaccines to treat the population for COVID. And I guess you could say if these worked, there would be a market for them for sure if they could provide protection against COVID-19. So this is an interesting one I just found, published in December. I think it was December. Preparation of a coronavirus nosode, which is a homeopathic treatment, from a clinical sample. So they found a patient who was positive with COVID-19, and they collected their saliva, and they diluted that a whole bunch of times. And they made nosodes from that, thinking that we can treat people safely and give them protection. You may be able to treat them safely, but you cannot give people protection with this. This is another interesting example of what appears to be a legitimate scientific publication. The journal is called the International Journal of High Dilution Research. Looks like a journal, has volume numbers, page numbers, has, I guess, numbers on the side, information for authors, readers, and so on. But it's completely non-scientific. It's a bunch of people with a belief who just created a lookalike journal, which gives credibility to people that want to sell these. So it can be very difficult often to distinguish legitimate scientific studies, now today more than ever. And by legitimate, I mean ones that are following the scientific method, that are peer-reviewed, that use double-blind studies, that use all these hallmarks of objective research. It's very difficult to often separate those, at least by appearance, from lookalikes or copycats like the one I'm showing you right now. Yeah, it was December 4th it was published. So yeah, don't take no-sodes. Doesn't work. Question, which of the following is not a central belief in the practice of homeopathy? Homeopathic preparations have become more potent as they are diluted. The law of similars, which says a substance that can cause a negative symptom can also be used to treat it when diluted. Homeopathic preparations are considered safe and effective by Health Canada. D, between serial dilutions, homeopathic preparations must be shaken in a specific way called succussion. Correct answer is C. They are considered safe as a supplement, but they are not considered effective, which is a requirement for selling medicine or drugs in Canada. It's not the case for supplements. So when you see those pills, the supplements, and all those things that are on there, those are basically unregulated from the perspective of whether they work to provide you any benefit or not. They're only regulated from whether or not they'll cause you direct harm. That's it. That's it for today's class. We're done with this unit. 3:42. Time moved quickly. Thank you very much, everyone that appeared in person and online. And this will be available online for you to watch a second time if you really want to, or if you are, of course, not with us at the moment. Great.